Contents of this particular session are: we will first compare the Fourier transform with Laplace transform. Then we will introduce Laplace transform. Then we will see there is a unilateral transform and a bilateral transform. We'll discuss what is the difference between unilateral Laplace transform and bilateral Laplace transform. Then we will discuss about the convergence of Laplace transform. We will then find Laplace transforms of all standard functions. Then we'll discuss the properties of Laplace transform and we'll prove some of the properties of Laplace transforms. Then we will do some example problems on Laplace transform. And then we will attempt a few previous gate questions. So these are the contents for today's session. So let us introduce Laplace transform. So in the previous sessions, we discussed about the Fourier transform. Now the question comes, what is the difference between Fourier transform and Laplace transform? Why, when there is a Fourier transform, what is the need for Laplace transform? Why should I go for Laplace transform? So here is the answer for all these questions. The Fourier transforms, they are extremely useful in many problems of practical importance. Wherever you have an LTI system involvement, you will find the use of Fourier transform. And if you have e power st, where s is j omega, if s is equal to j omega is taken, it's a purely imaginary complex exponential. What is meant by purely imaginary? There is no real part. Real part is zero. Suppose if you take s is equal to sigma plus j omega, and the real part is sigma and imaginary part is your omega, and if real part is zero, you will say that s is purely imaginary. A large class of signals can be represented as a linear combination of complex exponentials, and complex exponentials are eigenfunctions of a linear time invariant system. But the eigenfunction property applies to any complex number like s, not just purely imaginary. Okay, so this leads to the development of Laplace transform, where s is an arbitrary complex number. So s is an arbitrary, it need not be like a pure imaginary s, need not be a pure imaginary. And also you will find the use of Laplace and Z transforms in the analysis of unstable systems also. So we discussed in the previous session that we apply Fourier transform for signals with finite energy only, whereas you may apply Laplace and Z transforms for signals with infinite energy also. And you may do the analysis of system stability. This is what the importance of the Laplace transform, that they can be applied for the analysis of unstable systems, and they will play an important role in the analysis of system stability. That is what the Laplace transform significance. Now, let us define Laplace transform. Take a linear time invariant system. Then try to find the response of a linear time invariant system. You apply an impulse response with impulse response h of t to a complex exponential input x of t e power st is y of t is equal to h of s e power st, where s is a complex number. And how do you get capital H of s is equal to integral minus infinity to infinity h of t e power minus st dt. When s is purely imaginary, this definition will become Fourier transform. And when s is complex, this is the Laplace transform of h of t. So if s is purely imaginary, just now we discussed s is equal to sigma plus j omega, where sigma real part and j omega is the imaginary part. When s purely imaginary, substitute sigma 0, then capital H of S is H of j omega. But when S is complex, this is the Laplace transform, and S is equal to sigma plus j omega. So you'll have both real and as well as the imaginary parts for S, and hence it will become Laplace transform. So the Laplace transform for a generalized signal x of t, you may define it as capital X of S is equal to sigma integral minus infinity to infinity x of t multiplied with exponential function e power minus st dt. It is almost same as you may substitute, if you substitute simply S as j omega, it becomes Fourier transform. You observe x of omega t, x of t e power minus j omega t dt. That is nothing but your Fourier transform. So, if S is purely imaginary, the Laplace transform is same as that of Fourier transform. So the Fourier transform pair is represented by the symbol for x of t. The Laplace transform pair you may represent x of t, for which the Laplace transform is capital X of S, and for x of S the inverse Laplace transform is x of t. Hence x of t and x of S are called as Laplace transform pair. Now, the Fourier transform is the Laplace transform when S is purely imaginary. We may prove it also easily. An alternate way of expressing this is, now take S is equal to sigma plus j omega. So, Laplace transform capital X of sigma plus j omega is equal to integral, as per the definition, integral minus infinity to infinity x of t e power minus st. In place of S, here we have sigma plus j omega. So just substitute sigma plus j omega here. So it becomes very easy for us to divide this exponential term into multiplication of two terms as e power x plus y is equal to e power x into e power y. There is a reason why we are doing that. So x of t e power minus sigma t multiplied with e power minus j omega t dt, and you may take x of t e power minus sigma t as x dash of t. So take x dash of t, multiply it with e power minus j omega t dt. So you may take that x dash t e power minus j omega t. Now you apply the definition of your Fourier transform. Fourier transform of x dash of t is given by the equation integral minus infinity to infinity x dash of t e power minus j omega t dt. So you may readily write this equation as Fourier transform of x dash of t. So the Laplace transform is Fourier transform of the transformed signal x dash of t. So we established a relation between the Laplace transform and Fourier transform if S is a complex one. What is that S is sigma plus j omega. It is having both real and imaginary part. Then we are able to establish a relationship between the Laplace transform and Fourier transform, as the Laplace transform is the Fourier transform of the transformed signal x dash of t, which is given by x of t e power minus sigma t, where that sigma being the real part of your S. Depending on whether sigma is positive or negative, this represents a growing or a negative signal. If sigma is negative, e power minus of, again sigma negative, minus into minus plus. So it is exponentially raising or growing. And if you substitute sigma as a positive number, then e power minus sigma t, so it is exponentially decaying. That is a negative signal, you may say. Now we are now going to discuss the most important concept called region of convergence. So it is, what is region of convergence? It is defined as the range of complex variable, as in S plane, for which Laplace transform of signal is convergent. What is meant by convergence? It will have a finite value. is called convergence. So we are trying to find in what range the Laplace transform, for which Laplace transform of the signal is a finite value, is defined as the region of convergence. So we clearly understood what is the range of the Laplace transform of a signal, in which range the Laplace transform is finite. That range is said to be region of convergence. Now, let us discuss about different properties of region of convergence. ROC does not include any pole. So, if you take any a transfer function, that is the ratio of your output to the input. So the roots of the numerator polynomial and roots of the denominator polynomial are there. So the roots of your denominator polynomial are called roots of denominator polynomial are called poles. Roots of numerator polynomial as zeros. So now you are much aware ROC does not include any pole. For right-sided signal, ROC will be right side to the rightmost pole. For a left-sided signal, ROC will be the left side to the leftmost pole. So just not stating this, we will discuss these properties of region of convergence with example and as well as derivation, so that you may easily remember these, okay, and you may be able to apply them in the problems, in solving the problems. So that's what we are going to do. So we will discuss what is the ROC for a right-sided signal, and how do we find the ROC for left-sided signal. And for stability, ROC includes imaginary axis in S-plane. And for both sided signal, ROC is a strip in S-plane. And for infinite duration signal, ROC is the entire S-plane, excluding S is equal to 0 or plus or minus infinity. So we are here just listed 6 properties, and for all these properties, we are going to see the best examples, and we will thoroughly understand all these properties. So let us go for region of convergence. So it is defined as the range of complex variable as in S-plane for which the Laplace transform of signal is convergent or finite. So we made first property, ROC does not include any plane. Okay, so to the right hand side of the pole, observe, to the right side of the pole here, it is -1. You observe, this is -1. To the right side of this pole only we have shown here. So it is a right-handed side signal. Again, to the right side of pole here is 1, whereas pole here is -1. So to the right side of 1, this is the right side of this. This is the right side of pole -1. Similarly, you take the pole here 1, left side of this is the ROC. Here you have taken here -1, and to the left of it, this is the left side of this. I think you can understand it easily. Now, both sided signal. So both sided, what is meant by both sided? For right side signal, ROC will be right side to the rightmost pole. For left sided signal, ROC will be the left side to the leftmost pole. So just now we have seen 2 examples for right sided signal and as well as left sided signal. From that, for right sided signal, ROC will be right side to the rightmost pole. For left-sided signal, ROC will be the left side to the leftmost pole. So for stability, what is required for stability? ROC includes imaginary axis in S-plane. For both-sided signal, ROC is a strip in S plane. Just again, for our convenience, we have repeated the properties just now, whatever we have discussed, that properties of region of convergence. That's what again we have listed here. For a duration signal ROC is entire S plane excluding possibility of S is equal to 0 or S is equal to plus or minus infinity. Now let us take an example as we already discussed that we will see the right-sided signal and as well as left-sided signal with some example problems. So let us take x1 of t is given as e power minus at u of t, where a is an arbitrary real or complex number can be. Now right-sided signal. So mod of x of t is shown here. Okay. Similarly, mod of x of t as a function of t for real part of a greater than 0 and as well as real part of a less than 0. For both, it was shown. Now here, as per the definition of Laplace transform. What is the definition of Laplace transform? Capital X1 of S is equal to X1 of t e power minus st. What was given? X1 of t is given for us as e power minus at u of t. So hence, in place of x1 of t, we have written e power minus at u of t multiplied with e power minus st dt. This is what the definition of a Laplace transform. So now you have two exponential term with one is e power minus at, other one is e power minus st. So what can you do is you can take t as a common in both the exponential terms and you can add e power x into e power y, e power x plus y. So just take t as common and add this e power minus of s plus at dt. Now you may just evaluate this integral that will result in e power minus kt dt, integral e power minus kt dt, that is minus 1 by k e power minus kt. That is what the integral of e power minus kt dt as we are aware. So we have evaluated that integral minus 1 by k e power minus kt. Now substitute the limits, lower limit being 0 and upper limit being infinity. Now here what is the question? We started as per the definition of Laplace transform with the integral minus infinity to infinity. Now why we have changed the limits as 0 to infinity? If you do remember, your unit step signal u of t is defined for t greater than 0. So you must, and in place of u of t, you have taken it as 1 in the range 0 to infinity. And from minus infinity to 0 interval, that u of t is equal to 0. So I think this kind of problems and this discussion we already did in the previous session, if you remember well. So we are just changed those integrals 0 and infinity and then simply minus 1 by s plus a. Now you substitute the upper limit. Upper limit is infinity and lower limit is 0. So as a result, what is the result here? This convergence only if the real part of, so you can readily say this as 1 by s plus a if and only if real part of s plus a is greater than 0. That is, real part of s should be greater than minus of, see, if you send this a to the right hand side, it becomes minus a, and hence real part of s should be greater than real part of minus a, and we can write capital x1 of s, that is nothing but the Laplace transform of given x1 of t is 1 by s plus a when real part of s greater than minus real part of a. The ROC can be visualized using the S-plane plot shown here. The shaded region defines the values of S for which Laplace transform exist. The ROC is very important property of a two-sided Laplace transform. So you can observe that. So what is the ROC here? The region of convergence is the shaded portion that was shown here. This being the imaginary axis, RE corresponds to the real axis, and this is your region of convergence, whatever the shaded portion is there. And you observe here clearly minus A is written as S should be greater than real part of minus A. Accordingly, we have plotted the region of convergence. Now, we may take another example. See, earlier case it is e power minus at u of t. Now you take minus e power minus at u of minus t. See, earlier case u of t is there, and this case 1 by s plus a e power minus of s plus a into t, and now substitute the lower limit and upper limit, lower limit being minus infinity and upper limit being 0, you may get 1 by s plus a multiplied with 1 minus e power s plus a into infinity. And what is the solution? You may find that the region that this convergence is equal to e power b mod of t, and e power b mod of t. That may be written as e power bt u of minus t plus e power minus bt u of t. So you, as modulus is given, that may have the values like that. So if you find the inverse Laplace transform, you are going to get the value, the Laplace transform value as 1 by s plus b minus of 1 by s minus b. And if you simplify, you will get minus 2b by s square minus b square. For the first term, if you find the ROC, that is the real part of s should be less than b, and for the second term, the real part of s should be greater than minus b. And if you combine minus 2b by s square minus b square, b should be greater than 0 with the ROC shown as below. So you got the poles at minus b. How do we get that? Make s minus b 0. You will get s is equal to b as one pole. Again, make the other denominator of the other one, that is s plus b is equal to 0. You will get another pole which is s is equal to minus b. Now on the real axis, you just indicate the locations of the pole. One pole is indicated at minus b, another pole is indicated at plus b. So you may indicate, and your region of convergence is nothing but the shaded portion of this that lies between minus b and plus b. If b is less than 0, the Laplace transform does not exist. If you say b less than 0, the Laplace transform doesn't exist. So e power b 0, just substitute if b as 0, e power 0 1. So if b less than 0, the Laplace transform does not exist. Hence the ROC plays an integral role in the Laplace transform. That is what you can observe here. Now, the Laplace transform is a function of general complex variable, and for any given signal, the Laplace transform converges for a range of values of s. Just to now we discussed, this range is referred to as ROC and plays an important role in specifying the Laplace transform associated with a given signal. In particular, so we are summarizing whatever the observation we made. What is the observation we made? In particular, two different signals can have the same Laplace transform. can have Laplace transform with identical algebraic expressions. Just now we have seen for the left-handed and as well as right-handed, we got x of s as 1 by same s plus a only. But they may have the same algebraic expression and differing only in the ROC. Yes, region of convergence is different from for left hand sided signal and right hand sided signal. That is in the range of values of S for which the expression is valid. So that is what the important observation we made, that Laplace transform for two different signals may be the same, but their ROC will be definitely different. So the ROC is going to distinguish the two different signals. So of the Laplace transform. So let us take another example. Yes, just now we discussed this example, x of t is equal to e power minus at u of t. Yeah, if a is negative or zero, the Laplace transform still exists for this case. Now, let us take again the same which we have discussed, the Laplace transform. Again, why we are repeating is we are here having an important conclusion for the left-handed and right-handed signal. The Laplace transform expression is identical in both left-hand sided and right-handed side. Example one, which is similar but different signal. However, the ROC of S are mutually exclusive. Mutually exclusive means here real part of S is should be less than minus a for the case of minus e power minus at u of minus t, whereas real part of S is greater than minus a for the case of x of t is e power minus at u of t. So you observe this, real part of S is greater than minus a for the given signal e power minus at u of t, whereas for minus e power minus at u of minus t, real part of S less than minus a. So for Laplace transform, we need both the expression and ROC. That is what the important conclusion. Okay, the Laplace transform of the signal. We are asked to find the Laplace transform of a signal. The signal is given as sine omega t u of t. Now, as per the definition, modulus of x of s is x of s is the Laplace transform of x of t, is given by integral minus infinity to infinity x of t e power minus st. In place of x of t, we have sine omega t u of t. So for our convenience, we are writing sine omega t in the exponential form. The reason being that already we have e power minus st. So we can simplify this integrand. Hence we are expressing sine omega t as the summation of e power j omega t with e power minus e power j omega t. E power So, what is the meaning of bilateral Laplace transform? Is it is nothing but a two-sided transform. Okay, B corresponds B for bilateral or two-sided. It is also called as two-sided transform. Why do we say two-sided? Is it is getting extended as a bilateral Laplace transform is getting extended from minus infinity to infinity f of t e power minus st dt. Laplace transform of a bilateral signal f of t is given by fb of s. As it is a bilateral, just we had put here a subscript fb of s, and f of s is integral minus infinity to infinity f of t e power minus st. S is replaced with sigma plus j omega t, and you may separate these terms. As you are aware of, e power x plus y is equal to e power x into e power y. You are separated as two product terms here, e power x and e power y, and here you have written f of t e power minus sigma t multiplied with e power minus j omega dt. Consider the two-sided Laplace transform as the Fourier transform of f of t e power minus sigma t. That is the Fourier transform of an exponentially windowed signal. Note also that if you set the value of Laplace transform of f of s at s is equal to j omega, you have the Fourier transform. So if you substitute s is equal to j omega, just already we discussed. If s is pure imaginary, we Laplace transform is same as the Fourier transform. That discussion we already done. Now, now we will define one more Laplace transform called unilateral. So Laplace transform of x of t is given by x of s is identically equal to, you observe, the limits are taken as 0 minus 0 superscript minus. Okay, is the lower limit, upper limit is infinity. X of t e power minus st dt. So the transform will be written in uppercase letter. That is what we did. Capital S x of s defined from 0 minus 2 to include impulses at t is equal to 0. So 0 subscript minus, this is just an indication that we are including impulses at t is equal to 0 also. They are also impulses at 0 is equal to, at t is equal to 0 are also taken into account to indicate that we are writing the lower limit as 0 minus 1. S is equal to sigma plus j omega is a complex variable, fine, and S has units of inverse seconds, fine, and known as the one-sided Laplace transform, that is unilateral. There is also two-sided, which is bilateral version, just now we discussed, and the equation also once again for our convenience again reproduced here. We will only work with the one-sided version because it is easier to obtain the transient response, and also one-sided version is consistent with common practice and ignores x of t for t less than 0. So when do you use unilateral and when do you use bilateral? Unilateral transform is used when we choose t is equal to 0 as the time during which significant event occurs, such as switching in an electric circuit. Then you may use unilateral transform. And when do you use bilateral transform is the bilateral Laplace transforms are needed for negative time as well as they are also needed for positive time. So that is the difference between unilateral and bilateral. Now we have done a detailed discussion about the region of convergence, and we are asked about find the region of convergence. Say ROC and sigma is given. If sigma greater than minus 1, what is sigma? The real part of your S. S is equal to sigma plus j omega. The real part of sigma is greater than minus 1. Then it's what is its Laplace transform? The Laplace transform is x1 of s is equal to 1 by s plus a, for which the real part of s is greater than minus 1. Similarly, if the ROC, the real part of sigma less than minus 2, these two are given for us, and we are asked to plot the region of convergence, and we are asked to comment about its extension. So as we can see here, S is equal to minus 1. So a pole was clearly indicated at S is equal to minus 1, and we have taken two axes. This x-axis is here in our case is the real axis. Y-axis is our imaginary axis, which is represented by j omega. And one may indicate clearly the pole location here minus 1, and the region of convergence is sigma. It does exist for all sigma greater than minus 1. So you got whatever the region above sigma greater than minus 1 is your region of convergence. And now you are given the region of convergence straight away, sigma less than minus 2. So you have to work out with the sigma less than minus 2. So here you have to plot the pole at minus 2, and your region of convergence, as it is clearly given as sigma, that is less than minus 2. So this is less than minus 2. Whatever the region that is less than minus 2 is your ROC and gets extended. And now, suppose if you are given the region of convergence as minus 1 less than sigma less than 2, this is given. Now let us generalize this. So how do we generalize? Suppose we are given r1 and r2, r1 less than sigma less than r2, then your region of convergence is lying between, say, between r1 and r2. So how do we indicate? We already discussed, and this is a strip type, because you are going to get this in this is between minus 1 and 2 is your ROC, and you got a strip type, and your H of t is stable, and your uh, signal is a both sided signal. Okay, so I think you can better understand by this example, like you got a strip type ROC, and your H of t transfer function is stable, and the signal is a both sided signal, as just we have discussed. The Laplace transform, convergence of a Laplace transform. The Laplace transform does not converge to a finite value for all signals and all values of s. There is no rule that your Laplace transform converges for finite. Does not. It may not converge to a finite value for all signals and all values of s. The values of s for which Laplace transform converges is called ROC. Always include ROC in your solution. When you are asked about find the Laplace transform, you include the ROC also. Just we have taken the previous example, and here we have written 1 by s plus a, real part of s greater than minus 1, and here 0 plus indicates greater than 0 values, as you have written here. Why? U of t does exist for values between 0 to infinity. Remember, e power j omega is sinusoidal, thus only the real part is important for us. So, unilateral example of a unilateral transform, just whatever we discussed, that e power minus at u of t can be taken, and where it is 1 by s plus a, so 1 by e power minus at u of t. So the pole location was clearly indicated here. S is equal to minus a, and hence you may find the ROC as the shaded portion for this one. And now you take example of a bilateral Laplace transform, and e power minus at u of minus t. So you don't think that we are discussing these same signals. See, in the previous case we said left hand sided, right hand sided, and two sided. Now we are now saying about, and taking the same example, we are trying to understand unilateral and as well as bilateral Laplace transform. So take the example x of t minus e power minus at u of minus t, and integral minus infinity to infinity x of t e power minus st is given u of minus t tt, and we just now defined that u of minus t does exist between minus infinity to 0, and we substituted that. As a result, we got 1 by s plus a, and real part of s should be less than minus a, and we got light for such cases. So now you may take discuss the advantages of Laplace transform. You may find the solution to differential equations using algebra. So suppose a differential equation, a big differential equation is given, you may find very easily the solution making use of Laplace transform. Relationship to Fourier transform allows easy way to characterize a system. So there exists a relation between Laplace and Fourier transform, just now we discussed. That relation will be useful for us in order to characterize a given system. No need for convolution of input and differential equation solution. So there is no need of convolution, because convolution in time domain is equal to multiplication in frequency domain. As S domain is a frequency domain in Laplace transform, also just multiplication of transformed signals is sufficient, and it is an easier process rather than convolution. Useful with multiple processes in system. So you may find all these are advantages of Laplace transform. Now, how do you compute Laplace and inverse Laplace transform? Is suppose you are given a differential equation. Find the differential equations. You are given a system. For that system, you may write the differential equation. Then you may obtain the Laplace transform for that differential equation. E power minus st and du minus s e power minus st dt. Differential of e power minus st is e power minus st multiplied with minus s, and differential of v, which is sin t dt. dv is sin t dt, and v is minus, yeah, you may take that. And then therefore integral 0 to infinity e power minus st sin t may be written as minus e power minus st cos of t. Substitute the lower limit as 0, upper limit as infinity, minus s integral 0 to infinity e power minus st cos of t dt. So you may substitute the lower and upper limits, and you are left with minus e power minus st and cos of infinity minus cos of 0. So you may get 1, and here minus s integral 0 to infinity e power minus st cos of t. Now again it is of the form u. We take u as e power minus st and du as s e power minus st, and v as this, and dv as cos t dt, and v will be sin t. So making use of that, one may find finally integral 0 to infinity e power minus st sin t dt is resulting in a Laplace transform value of 1 by 1 plus s square is the value. Now, we may list the Laplace transforms for standard signals. Just now we computed it for 1, we got it as 1 by s. We proved for e power minus at as 1 by s plus a. We proved the same for cosine and sine functions as s by s square plus 1. S by generalized is s by s square plus omega square. If we are having omega here, in our case omega is equal to 1, you may substitute cos omega t, and omega being 1, we derived this s by s square plus omega square. In place of omega we have 1. Similarly, s square by 1 by sine of t. Do remember here variation. Here s by s square plus omega square, here 1 by s square plus omega square. So here you may get 1 by s square plus 1. And here x of t is t power n, and x of s is t power n means nth power t. And you may, we are going to see this x of s as n factorial by s power n plus 1. We are going to prove this also. And use of this particular, this you may observe. Suppose you substitute n as 0. X of t is u of t. Then x of s is 0 factorial by s power 1, which is 1 by s. N is equal to 1. Then 1 by s square. N is equal to 5. Then x of s is 5 factorial by s power 6, which is nothing but 120 by s power 6. Anyway, we are going to prove these things. Yeah, in the earlier case, just we discussed about the Laplace transforms of given signal only. Now here we are going to discuss the Laplace transform along with their ROC also. Delta of t is given, and its transform, okay, and ROC. So here sometimes instead of Laplace transform of f of t is indicated as f of s. Okay, f of t is your given function. Laplace transform of f of t is capital F of x. This is the same notation can be used. Like if x of t is your input signal, Laplace transform is indicated with x of x, capital X of s. Okay, am I right? So your region of convergence will be all s, entire s for delta of t. And if you take a step function, delta of t, you are aware it is impulse. U of t is step function. It is 1 by s. So the real part of s should be greater than 0 is your region of convergence, ROC. T is taken, f of t is t. Your Laplace transform is 1 by s square. Your ROC is real part of s greater than 0. T power n factorial by s power n plus 1. Real part of s greater than 0. E power minus at. Your Laplace transform is 1 by s plus a. Real part of s should be greater than minus a. And if you take t into e power minus at, 1 by s plus a whole square, and the real part of s should be greater than minus a. You may extend it for the nth time, t power n e power minus at, n factorial by s plus a whole power n plus 1, and real part of s should be greater than minus a. So you observe for all these cases we got the same ROC value. Now cos bt, s by s square plus b square, real part of s should be greater than 0. E power minus at sin bt, b by s plus a whole square plus b square. E power minus at cos bt. It is s plus a divided by s plus a whole square plus b square. And real part of s should be greater than minus a. T sin bt. You will get this. So we are going to prove all of these, and we are also going to prove the properties of Laplace transform. And during the property itself, we are going to get the multiplication by t power n, integration, differentiation, whatever the results, Laplace transform results we have tabulated. We are going to prove all of them. The first property being linearity. Let us take the linearity property of Laplace transform. So the linear property is given by Laplace transform of c1 x1 of t plus c2 x2 of t is given by c1 x1 of s plus c2 x2 of s. What is this property is called linearity property, and it is satisfying superposition principle. If you remember properly, superposition is again combination of additivity and homogeneity. So we have checked whether the given system is linear or not by checking for the condition of linearity, superposition principle is satisfied or not, whether we have getting the additivity and homogeneity combined properties or not. We have done it already. Now take the Laplace transform of c1 x1 of t plus c2 x2 of t. And as per the definition, integral 0 to infinity x of t e power minus st. In case of x of t, we have integral this c1 x1 of t plus c2 x2 of t. Just we substituted. Now separate these as two different terms, and we may readily prove integral 0 to infinity x1 of t e power minus st as x1 of s, and this as c2 x2 of s. Now we may use the linearity property for finding Laplace transform of sine hyperbolic t. Sine hyperbolic t is given by 1 by 2 as per the definition, 1 by 2 e power t minus 1 by 2 e power minus t. And one may write this as 1 by 2, separate them, Laplace transform of e power t minus 1 by 2 Laplace transform of e power minus t. And one may write as we just proved it as 1 by Laplace transform of e power at is 1 by s plus a, s minus. So here you, in place of a, e power minus at we proved. So in place of a we have plus 1. So for e power minus at it is 1 by s plus a. But a is here plus 1. Hence you will get minus here. E power minus t. So in place of a we have 1. So here you will get s plus 1. So as a result, we proved Laplace transform of sine hyperbolic t as 1 by s square minus 1. Now, we are now going to make an important conclusion. If Laplace transform of x1 of t is x1 of s and its region of convergence is R1, for another signal, time domain signal x2 of t, and its Laplace transform is x2 of s and region of convergence is R2, then as per the linearity property, a1 x1 of t plus b x2 of t is your time domain signal. Its Laplace transformed signal will be a x1 of s plus b x2 of s. And the region of convergence is the intersection between R1 and R2. ROC is R1 intersect with R2. This follows directly from the definition of the Laplace transform, as the integral operator is linear. It is easily extended to a linear combination of an arbitrary number of signals. So we have done a ROC exercise for the linearity. If we know the ROC for x1 of t as R1, ROC for x2 of t as R2, then ROC for R1 intersection R2 is, what is it? ROC is R1 intersection R2. That is what we have shown. Now, let us take another important property of Laplace transform. And you observe that we will discuss the property example problem based on the that particular Laplace transform property. So that what happens is we will be able to remember that we are proving that property and we are making use of that property in solving a problem, so that will be remembered by us very easily. So if you scale a function, a time scaling, you x of t is your original signal, x of t is time scaled by a, so x of at it becomes Laplace transform of x of at is integral 0 to infinity x of at e power minus st dt. U is equal to at, t is equal to u by a, dt is equal to 1 by a du, and 1 by a integral 0 to infinity x of u e power minus s by a u du. As a result, you may show that readily as 1 by a capital X of s by a, capital X being Laplace transform of x of t. So we have proved the scaling property. Laplace transform of x of at is 1 by a x of s by a. Now we will make use of that Laplace transform of sine omega t can be written as that 1 by omega, and it can be written as this 1 by omega square by s square plus omega square. This can be shown as 1 by omega multiplied with 1 by s by omega whole square plus 1. So as per the scaling property, and we may prove Laplace transform of sine omega t as omega by s square plus omega square. Similarly, let us take a property called time shifting property. The signal x of t is time shifted by a factor of t naught. Signal x of t is time shifted by a factor of t naught, and u of multiplied with u of t minus t naught. Then what is the Laplace transform? So Laplace transform of x of t minus t naught with u of t minus t naught is, in place of x of t, we have x of t minus t naught multiplied u of t minus integral limits with t naught and infinity in place of 0 and infinity. So you have written here x of t minus t naught, u of t minus t naught is 1 between t naught, between the integrals, between the limits of the integral from t naught to infinity. So x of t minus t naught e power minus st dt, and u is equal to t minus t naught, so that you may get the new limits, and you may substitute that. Take t minus t naught as u. So you may write, instead of x of t minus t naught, you may write x of u. E power minus s, in place of t, one may write u plus t naught, and yes, du. As we are writing x of u, so it is du. So e power minus st naught can be brought outside the integrand. So bring that outside the integral. Integral 0 to infinity x of u e power minus su du, and that will result, as per the definition of your Laplace transform, this x of u e power minus u du, integral 0 to infinity, is nothing but the definition of your Laplace. So you got it as e power minus x of s, in our case is s plus a. So we have written this as e power minus 10s divided by s plus a. So this is time shift property of Laplace transform. Now let us take another example. Another property is frequency shift property. So e power minus at x of t x of s plus a. So on the other side you have a shift. Other side means S domain side, frequency domain, capital X of S plus A. So you take the Laplace transform of e power minus at x of t, integral 0 to infinity e power minus at x of t e power minus st dt. So integral 0 to infinity x of t e power minus of s plus a t dt. So one may readily show this as capital X of s plus a. So you have a frequency shift in the s domain. So if you are given e power minus at sine omega t, you may use this frequency shift property, and you may write omega by power n integral 0 to infinity x of t nth derivative of dou n dou sn of e power minus st dt. We are writing like this. So minus 1 whole power n dou n by dou sn integral 0 to infinity x of t e power minus st dt, and that can be shown as minus 1 whole power n nth derivative with respect to s dou n by dou sn x of s. And making use of this multiplication property, we may write Laplace transform of t power n u of t as minus 1 whole power n d by ds derivative dn dsn of your x of s. In our case, it is 1 by s, and you may show this, that is equal to n factorial by s power n plus 1. We may again make use of this multiplication property once again in solving the example problem. We'll discuss again in detail again there. Laplace transform of time differentiation property. So differential of f is indicated as f dash or f superscript n. whatever here f superscript 1 is shown, that is differential of f. Do remember. So f of t is your original function. Differential of f of t is represented as f dash of t. So this is your f dash of t. That's how you are indicating. Laplace transform of f dash of t is equal to f dash of t into e power minus st dt is the Laplace transform. Integral 0 to infinity, fine. F of t, integral 0 to infinity, integral f dash of t, e power minus st. F of t, e power minus st. And integral 0 to infinity is that. So, and this is of the form. Again, if you remember, of the form integral uv. So, we have already worked with that integral uv form, and we have proved that also, and we may get two integrands. That's the reason why you got here two integrands, if you observe carefully. So the limits being 0 to infinity, and yeah, so you may substitute the lower and upper limit. So here f of minus f of minus 0 minus, how do we get that? E power minus infinity is 1 by e power infinity. 1 by infinity value, you are aware of it. That value is 0. E power 0 will result in 1. And f of 0 is, yes, in place of t is equal. So if you substitute f of 0, you will get e power minus s into 0. E power 0 is 1, and e power infinity is vanishing. E power minus, so you got the result due to the lower limit as minus f of 0 minus plus s integral 0 to infinity f of t e power minus st. As a result, we got s f of s. So how we have written f of s? As per the standard definition of Laplace transform, integral 0 to infinity x of t e power minus st dt is capital X of s. In place of x of t, we have f of t, and f of s is the Laplace transform. So s into capital F of s, where f of s is the Laplace transform of f of t minus f of 0 minus. So this is what the Laplace transform of a derivative. If f dash t is the derivative of f of t, we may show that Laplace transform of f dash of t as s into Laplace transform of f of t, which is nothing but f of s into capital F of s minus f of 0. This is what the Laplace transform of a derivative. The general case is shown with an induction. So just we have done it for f dash. You may extend it for f double dash, f triple dash, and nth derivative. So if there is an nth derivative, Laplace transform of fn of t, that means f dash is the first derivative, f double dash second derivative, f triple dash third derivative, and so on. And the function f of t has nth derivative as fn of t, and that is given by sn f of s. So that can be written as, you may substitute the values of n from 0 to n minus 1, substitute, and you may get minus s power n minus 1, f of 0 minus 1, and so on, f of n minus 1, 0 minus 1. And yeah, this is what Laplace transform of time differentiation property. If you have g of t as f of t u of t, then all the initial values like g of 0, g dash of 0, g double dash of 0. That means all the initial values of the differentials, double dash of 0, g n of d dash of 0 is 0. So thus the formula we may apply, and thus the formula simplifies as Laplace transform of g power n, nth derivative of g of t is given by s power n into Laplace transform of f of t. So your g of t is given as f of t u of t, and nth derivative of g of t is s power n f of s. The derivative is more complex. So if you have a single derivative, d by dt of g of t is f dash of t u of t plus f of 0 delta of t. F of 0 delta of t is the one that we got. So we have highlighted that f of 0 delta of t. Okay, we may use this property. Yeah, Laplace transform time differentiation property in solving such problem. If g of t is cos of t u of t, in it is again g of t is, just now we discussed, g of t is f of t u of t. In place of f of cos t is sin t. So we have written sin t, and u of t as it is plus delta of t and f of 0. Okay, and we may use this property. Okay, and then one may say f of 0 is f of 0 delta of t. So you may write that as delta of t. And here you may substitute why f of 0 is 1, f of t is cos t. Cos of 0 is 1 in our case, in this particular example. Hence, your f of 0 is equal to 1. As f of t is equal to cos t, cos of 0 is being 1, we have simply written it as delta of t. And you may plot this. Now, from the Laplace transform time differentiation property, it can be demonstrated that the Laplace transform of derivative is the Laplace transform times s. That is, f dash of t is g of t implies s into f of s is capital G of s, where capital G of s being the Laplace transform of g of t, and capital F of s is the Laplace transform of f of t. We may do that. We have the following commutative diagram. Suppose Laplace transform of differential of t power n u of t is, you may write d by dt of t power n u of t can be written as s into Laplace transform of t power n u of t. Where d by dt of this as s. So you have written that as s into Laplace transform of t power n u of t. And that can be written as, we just now proved Laplace transform of t power n u of t as n factorial by s power n plus 1. Already s is here, s multiplied with 1 by s power n plus 1 into n factorial. What is the result? N factorial by s power n. Take another way. In t power n can be written as t power d by dt of t power n u of t can be written as Laplace transform of n into Laplace transform of t power n minus 1 u of t. And if you observe again, Laplace transform of t power n minus 1 u of t is again n factorial by s power n. So this is based on this. The Laplace transform of a derivative is the Laplace transform times s. That means s into f of s is g of s. We proved that. We now have the following commutative property. Suppose d by dt of t power n u of t in here, this is we are applying for trigonometric functions. There we have taken t power n. In place of t power n, we have sin t u of t. Laplace transform d by dt of sin t ut is s into s times Laplace transform of sin 2 t u of t. We said same s times s into Laplace transform sin t ut is 1 by s square plus a square. In place of a, we have 1. So s by s square plus 1. Take another way. Differential of d Laplace transform of d by dt of sin t u of t is same, may be taken as Laplace transform of, for this one, Laplace transform of cos t u of t. Here we did for Laplace transform of differential of sin t u of t. And now we are computing Laplace transform of cos t u of t is s by s square plus 1. So the Laplace transform of cos t u of t and Laplace transform of differential d by dt of sin t u of t both are resulting in the same Laplace transform. You observe that. Now, Laplace transform differentiation of trigonometric functions. We said that, just now we have done this. Now we now have the following commutative property, d by dt of e power minus a t u of t. And we may prove that as s by s plus a. Similarly, Laplace transform of minus a e power minus a t u of t plus delta of t as s by s plus a. Again, take another commutative diagram, d by dt of sin omega t u of t as s times the Laplace transform of d by dt of f of t u of t is s into f of s. That is what we are doing here, s into f of s. What is f of s? Laplace transform of sin omega t u of t. So you are doing this. S into omega by s square plus omega square. And here you may take omega into Laplace transform of cos omega t u of t. And you are going to get the same again, omega s by s square plus omega square. And now, again another commutative diagram, Laplace transform of d by dt of cos omega t u of t is s times L of cos omega t u of t, which may be shown it as s by s square plus omega square. Instead of this, you may take a Laplace transform of minus omega cos sin omega t u of t plus delta of t. That also results in the same s square by s square plus omega square. So Laplace transform of dx of t is equal to s into x of s minus x of 0 plus. Now let us prove this Laplace transform of d of x, so that means differential of x of t, capital D, is differential d by dt of x of t e power minus st dt. And let us take u as e power minus st, du as minus s e power minus st. And you may show this as s into x of s minus x of 0 plus. We proved this. Substitute the lower and upper limit. You will get s into x of s minus x of 0. So you are asked to Laplace transform of differential of cos t. That may be shown as s into x of s minus x of 0. S into x of s. What is x of s? Is the Laplace transform of your this. So it is s by s square by s square plus 1 of x of 0 plus. That x of 0 plus in our case is 1. So you may simplify that as minus 1 by s square plus 1, which is same as Laplace transform of minus sine t. Laplace transform of minus sine t. So Laplace transform of differential of cos t is same as Laplace transform of minus sine t. Laplace transform of differential of cos t is same as Laplace transform of minus sine t. That is what we have proved. Now, let us tabulate whatever the properties we have seen. Linearity property. Yes. A1 f1 of s plus a2 f2 of s. Laplace transform of derivative of a function. Just now we had discussed, we proved it as s into f of s minus f of 0. Laplace transform of nth derivative is s power n f of s minus s power n minus 1 f of 0 and so on. S into f power n minus 2 0 plus and so on. Integral. Laplace transform of integral 0 to 1 f of tau d tau is given as capital F of s by s, where capital F of s is the Laplace transform of f of tau. And real shifting, that is, you shift it by a factor of t naught, f of t by a factor of t naught, f of t minus t naught, u of t minus t naught will result in e power minus t naught sigma f of s, t naught s, e power minus t naught s into f of s. Okay, and s can be sigma plus j omega. Okay, if it is a complex. Okay, and Laplace transform of e power minus at f of t is the complex shifting property that can be shown as f of s plus e. And we are going to discuss this initial value and final value. Just for our convenience, we have tabulated this one. 7th and 8th, we are going to prove them. And multiplication by t is resulting in d by ds of f of s, first derivative. And yeah, you may continue it for up to nth derivative. That can be done very easily. Time transformation. So what is time transformation is Laplace transform of f of at minus b u of at minus b. It is called time transformation. Take the inverse Laplace transform of f of at minus b u of at minus b. Inverse of f1 of s into f2 of s is integral 0 to t of t minus tau f2 of tau, and integral 0 to t f1 of tau f2 of t minus tau d tau, and Laplace transform of f of tau t is given by time periodicity property, and that is given by 1 minus e power minus st f1 of s, where f1 of s is integral 0 to t f of t e power minus st. Now we will take some examples, unilateral and bilateral versions. And here, for the standard functions we are talking about, we did for e power minus at u of t. And for e power at, if you do it, it is 1 by s minus a, and the real part of s is greater than plus a. And now we are given f of t as delta of t minus t naught. That is your impulse shifted, time shifted by t naught. Write that as integral delta of t minus t naught multiplied with e power minus st, and as delta of t minus t naught is 1 in the interval 0 to infinity. So you may take that as integral 0 to infinity e power minus st dt, and you have to substitute your t naught here. So f of t is equal to delta of t. We use the multiplication property. If you do remember, we may use multiplication property. What is that multiplication property? F of t delta of t minus t naught, integral 0 to infinity f of t delta of t minus t naught is f of t naught. In place of f of t we have e power minus st. So f of t naught means f of t is e power minus st, f of t naught will be e power minus st naught. That is the reason why here you got e power minus st naught. One may easily understand that. Now f of t is given as u of t. We may take unit step, unit impulse, unit ramp, all our standard signals, and then we are trying to find the Laplace transform of those standard signals like impulse, step, and what we are going to get as the Laplace transform of impulse, Laplace transform of step, Laplace transform of impulse. Just now we proved it as 1 for all values of s. Now let us try to prove it for what? For the step function u of t. And capital F of s is, as per the definition, integral 0 to infinity f of t e power minus st dt. In place of f of t, we are given u of t. Just substitute u of t e power minus st ut, and minus 1 by s, limit t tends to infinity e power minus st minus 1, and so on. And that is going to result in a value of minus 1 as limit t tends to infinity e power minus of sigma plus j omega t, and so on. So that will result in a value of 1 by s for all real s greater than 0. That is what we proved. Then another example problem, cos bt and sin pt. We said that in the tabular form we are given Fourier transform of cos bt as s by s square plus b square. We are proving it. How? Just take cos bt as the summation of e power j omega t plus e power minus j omega t divided by 2. Expand e power j omega t, cos omega t plus j sin omega t. I am talking about this cos bt. So e power j bt, you write. As a result, cos bt plus j sin bt. Here cos bt minus j sin bt. Add these two terms, 2 cos bt divided by 2 cos bt. Hence, you may write the Fourier transform of that as, for e power minus at, we are aware it is 1 by s plus a. In place of minus a, we have b, jb, we have jb in place of minus a. So we may write 1 by 2 is already here. We may write Fourier transform of e power j bt e power minus st, that is resulting in s minus j here. Yeah, the first term, and we may write that 1 by 2 s minus jb, and for the second term, which is 1 by 2 e power minus j bt, we may write 1 by 2 s plus jb. As a result, we have got s by s square plus b square, and the real part of s should be greater than 0. Now take f of t as sin bt, making use of the same e power j bt minus e power minus j bt. As a result, 2j sin bt we will get. Subtracting e power minus j bt from e power j bt, we will get the result of 2j sin bt divided by 2j. So you are left with sin bt. So make use of the same technique, whatever here, use it. We will be able to get the Fourier, the Laplace transform of sin bt as b by s square plus b square, and a real part of s greater than 0. Now take e power minus at cos bt as the given function and find the Laplace transform of this given function. Again the same technique we may use. Cos bt will be replaced with e power jbt plus e power minus jbt, and we may show that Laplace transform of e power minus at cos bt as s plus a divided by s plus a whole square plus b square. And these properties are very, very useful for us in solving the problems. Example of bilateral version, we said bilateral e power at u of minus t, and as a result, if for f of t e power at u of minus t, we are going to get the value of Laplace transform as minus 1 by s minus a, and real part of minus s should be greater than minus a, and minus of 1 by s minus a. Real, real part of s should be less than a. You observe, real part of minus s greater than minus a. Multiply on both sides with minus. What happens? The inequality, if I multiply an inequality greater than with minus, it becomes less than, right? So real part of s less than a is the result. Similarly, we are given minus e power minus at u of minus t. Yeah, so you may work out with this, and you are left with real part of s less than minus a. Note that the Laplace can also be found for periodic functions. Okay, now based on these concepts, one may do the problems on Laplace transform. You are asked what is the Laplace transform of the waveform shown in the below figure. Figure is given. You may write the given function f of t as the sum of step functions u of t with unit amplitude u of t minus 1 minus 2 u of t minus 2. You observe here from 0 to 1 it is having an amplitude of 1. From 1 to 2 it is having an amplitude of 2, and yet t is equal to 2 it is having an amplitude of 2. So your answer is f of t can be written as u of t plus u of t minus 1 minus 2 into u of t minus 2, and you may find the Laplace transform of u of t as 1 by t, u of t minus 1 as e power minus s by s, and u of t minus 2 as e power minus 2s by s. Already here, before u of t minus 2, you have minus 2. So you may multiply it with minus 2. So one may easily find the Laplace transform. Now, you are asked to find the Laplace transform of the following signal and ROC. x1 of t is given d square by dt square of e power minus 3 t minus 2 u of t minus 2. And you may find the solution in an easier manner. X of t, taking x of t as e power minus 3t u of t. Suppose if you take x of t as e power minus 3t u of t, then the Laplace transform for that is defined as 1 by s plus 3 and sigma greater than minus 3. Now you do the time shifting x of t minus 2. Okay, y of t is x of t minus 2. So y of s is for a time shifted by a factor of t naught. It is just now we proved that e power minus s t naught. We proved this property. If x of t is time shifted by t naught, x of t minus t naught, we proved Laplace transform of x of t minus t naught is e power minus t naught s. T naught s, where t naught is the amount of time shift. In this case, that t naught is 2. So we will write e power minus 2s x of s minus e power minus 2s by s plus 3. So we may write the y of s equation as this. So x1 of t is e power minus yes d square by dt square of y of t. This can be taken as x1 of t. How do we get d square by dt square of y of t? And yeah, it is x1 of s is the Laplace transform. For a second derivative, it is s square of ys, y of s, s square of y of s. For the nth derivative, it is s power n y of s. For the first derivative, it is s into y of s, making use of differential property. Here we are applying differential property. If you remember, whatever we just now read, and s square, and we already found y of s, which is e power minus 2s by s plus 3. So just apply that. You may get the solution. Now we said that in the tabular form we mentioned initial value theorem and final value theorem. Let us define initial value and final value theorem so that we may make use of these theorems in solving the problems on Laplace transform. So how the initial value theorem is given? The initial is given by x of 0 is equal to limit s tends to infinity s into x of s. And the condition being it is applicable only for causal type signals. Okay, that is what is meant by causality. X of t does exist for all values of x of t is non-zero for t greater than 0. And x of t is 0 for t less than 0. That means for negative value of t, x of t does not exist. That is called causality. So that is one important point that need to be remembered. And final value theorem. How do you define final value theorem is x of infinity is limit s tends to 0 s into x of s. And what is the condition? It is applicable only for causal type signal. Again, final value theorem also is applicable only for causal type signal. Both initial value and final value theorems are applicable only for causal type signal. That means your x of t has a value for all values of t greater than 0. X of t is 0 for all values of t less than 0. That is what the causality condition. Apart from that, in the final value theorem, one more important point, s multiplied with x of s, that is your transform, Laplace transform, s multiplied with Laplace transform should have only left hand side poles in s plane. It should have only left hand side poles in the s plane. Okay, that means there should not be any right hand side poles for s into x of s. So based on these conditions, we may take problems on initial value and final value theorem. And f of s is given for us as 1 by s square plus 1. And f of s and f of t are the Laplace transform pair. And we are asked f of small f of infinity. Now, as per the definition, f of infinity, if we apply s into f of s is, we may observe that s by s square plus 1. S square is minus 1. If s square is minus 1, s is equal to plus or minus j. Poles, that the poles s is equal to plus j and s is equal to minus j. They are not equal to left hand side poles. We have poles that does exist on the right hand side. So what is the condition for final value theorem? S into x of s should have only left hand side poles in the s plane. But is it so? No. The poles are also lying on the right hand side. So one cannot apply final value theorem in this case because s is equal to plus or minus j. The poles are not on the left hand side. So you may use f of, so you may not apply the final value theorem. F of t is equal to sine t u of t, and f of infinity can be found as sine infinity u of infinity. And as we cannot apply final value theorem, you have to follow like this. F of t is sine t u of t. We have done f of s. We are aware f of s is 1 by s square plus 1 for f of t is equal to sine t u of t. So we use that result here. Okay, that is the reason why you should be thorough of all the Laplace transform of standard functions. Then it's easy for us to solve such problems. So here you can substitute. You are asked for f of infinity. So in place of t, you may substitute infinity. So sine t for t infinity, sine infinity u of infinity. So sine of theta, any highest value of theta, always the value of sine lies only in between minus 1 and plus 1, and u of infinity is equal to 1 for all values of u of t is equal to 1 for all values of t greater than 0. So as a result, your f of infinity is minus 1 less than or equal to f of infinity less than or equal to 1. That is the range of your sine function, sine infinity. So that is what you can say. And now again you are given f of s is here, f of t and capital F of s are the Laplace transform pair. This is not equality, it is a arrow mark in order to indicate what f of t and f of s are Laplace transform pair. There will be an arrow. So you should be cautious of typographic mistakes. So 1 by s into s minus 1. You are asked for f of infinity. Signal is so f of infinity. The signal is causal because dependent on past value of s minus 1. Yes, if you observe this one, s is equal to 0, s is equal to s minus 1 0. So you observe that f of s has the terms that depends on only present and past values. There is no dependency on the future values. So s into f of s, s into f of s is s 1 by s into s minus 1 in denominator. So s and s get cancelled and you will be left with 1 by s minus 1. poles S is equal to 1, not equal to LHS plane. Poles lie on the right hand side. So you cannot apply final value theorem. So why this we are discussing is the moment if anyone sees f of infinity value, they may readily think, they may mistake easily that I may apply final value theorem. Okay, but you should be cautious. I'll be able to apply final value theorem for this or not. For that, the best check is just whenever final value theorem you want to apply, you need to check poles, all the poles, whether the poles are lying on the left hand side or not. No. So FV of t, FVT is not applicable. That is, final value theorem is not applicable. So f of s is equal to 1 by s into s minus 1, and that can be written in the form of partial fractions as 1 by s minus 1 minus 1 by s. One may readily write inverse Laplace transform of minus 1 by s as u of t. Laplace transform of 1 by s minus n 1 as this we proved, e power at u of t, a being e power minus at u of t, and a being here 1. So you may get that e power t u of t minus u of t. What is asked for us is f of infinity, so you may substitute that. So you got minus 1 plus infinity, and as a result, to infinity you add anything is in infinity only. So f of infinity is infinity. So you got that. Now we are given, for example, we are given a waveform. What waveform is given? A waveform with an amplitude 1, and the waveform is getting extended from 0 to 3. X of t is given, and on the x-axis you have time period t, and it is getting extended in between the limits 0 to 3. Amplitude is 1. This is what is given, and we are asked Laplace transform of f of t, that is capital F of s is what, and the region of convergence is what? Question mark is given. Now let us try to do this. F of t is 1, and your integral limits should be 0 to 3 as clearly given in the problem itself, and 1, replace f of t with 1 as its amplitude is 1 between 0 to 3. So substituted that e power minus st dt, that is equal to e power minus, so it is of the form integral e power minus kt dt is integral of e power minus kt dt is e power minus kt by k. So e power minus st by minus s, and you may substitute the limits here. The upper limit are being 3 and lower limit 0. You will get simply 1 minus e power minus 3s by s. At s is equal to 0, you may substitute now the s is equal to 0, f of 0 you may get. If you substitute s as 0, f of 0, capital F of 0 is 1 minus e power minus 3s by s, 0 by 0. And so you have to use L'Hospital rule. What is that L'Hospital rule is? If you have numerator and denominator, that is resulting in a value of 0 by 0, take the differential of numerator and independently and take the differential of denominator. So differential of numerator is differential of numerator d by ds of 1 minus e power minus 3s. That is resulting in 3 by 3 multiplied with e power minus 3s. Differential of s in the denominator with respect to s, ds by s, d by ds of s is 1. That is differential of denominator. Differential of numerator, which is 1 minus e power minus 3s, is resulting in 3 e power minus 3s. And at s is equal to 0, you substitute s value 0 here. 3 into e power minus 3 into 0, e power 0 is 1. So 3 into 1. So you got capital F of 0 as 3. Now you substitute the other limit, s is equal to infinity. Capital F of infinity is resulting in e power infinity, e power minus infinity, not infinity. Okay, so 1 by infinity is you are getting a value of 0, yet s is equal to minus infinity. F of minus infinity is 3 e power minus 3s, yet s is equal to. So you observe, you should be very cautious here, as e power minus infinity and e power plus infinity both are different, as e power minus x is 1 by e power x and e power x is in the numerator itself. E power minus x value is 1 by e power x. If at all, if that 1 by infinity, it will result in 0, and e power plus infinity, that will result in infinity. So ROC, the entire S plane, one may conclude, excluding S is equal to minus infinity. So this is the problem, and I had uploaded, I have sent the PPTs. In due course you will get. I am assuring you that we will upload all the PPTs, whatever we discussed in the sessions here. I am trying to make the session PPTs the best, whatever I can give. So that's the reason why in due course you will get. You need not worry that we are not getting the PPTs. So they are under the process. You will get you may get more benefited. Once again, I thank all the authorities for giving me this opportunity. I wish you all the best. Please do practice all the problems which we have discussed in the session. Thank you. We'll meet in tomorrow session again.